Okay, start.
Okay. So, guys, this will be like a very basic introduction to machine learning. I'll not be going like super deep. So, let's see what is machine learning, right? So, it makes decisions
Are
on
you sharing
data
a
without
screen,
being.
Paul?
Oh yeah, of course. Sorry, I forgot. Can you see the PPT?
Yes.
Yeah,
Yes.
So the basic, let's start, right? So what is machine learning and how is it different from AI? So machine learning makes decisions based on data without being explicitly programmed, which basically means that it doesn't actually have hard coded like if and else statements which make it do certain things. It's completely based on like algorithms and such. So, what are the key characteristics of machine learning? Well, there are a lot, but I'll just be covering three best, uh, the best three to be known. So, the first is that it learns from data, and it can improve based on how much data you give it. So that's why companies nowadays are very hungry for data because that's very powerful, and data can have a lot of influence on how good your model is actually. And it a good model should generalize on that given data. So it should be too of it on the data that we give, but it also shouldn't be completely unrelated. It should strike a good balance between. And as I've said, it isn't explicitly programmed, unlike traditional programs where we have to code each and every line. Here, the model learns by itself based on certain algorithms that we code. So, what is a model? We've been talking about ML models, right? A machine learning model is a certain type of AI model, which is in on itself a type of framework. While AI is a broader field, machine learning is a subset, which focuses on creating systems that can learn by itself or with amount of input by from us. So basically, there are three types of three types of machine learning models. Not only three types, but the most well-known are these three. So supervised, which learn from labeled data, unsupervised, which learns from unlabeled data and tries to find patterns in these unlabeled data. And third, but not least, reinforcement learning, which learns through interactions with the environment. What is an environment? We'll basically cover like a very basic understanding of it later on. So there is somewhat of a this is somewhat of a pipeline of how we create an ML model. So at first we collect the data, be it from websites or basically the whole internet can be used to collect data. Then we have to clean the data. It's not supposed to be data cleaning, not data clearing. So as you know that real life data doesn't actually, it's not perfect. It has like missing values and like errors. So we have to clean all of this and thus create like a good enough data that our model can actually learn from this. And after that, we perform something called EDA or exploratory data analysis of the data, which allows us to find correlations between different data like features. Features is basically one column of data, be it Like for example, if we are trying to predict the house price, we might have features like the area, the price, the area, the how many rooms there are, and how many floors there are. So these are all features. And exploratory data analysis tries to find what the correlation are. And if there are like zero correlation, we eliminate these from the data because it's just unnecessary.
Is it the other way around? If there is more correlation, that means there is no much
So yeah,
information
we
gained
have
from the data, right? Is it the
yeah, we
correlation
have to
between the
find
target or between the features that you are talking about?
correlation between the features itself. So how related are some of yeah. Actually, you're right. Target is what we are trying to find the correlation between, not the features itself.
Mm-hmm.
So if we have to see how correlated these are. If there is no zero correlation, we have to remove it
Yeah.
since it has no use.
So if it has zero correlation, so say there are five features and three out of five have no correlation with the target, what we are predicting, then it is of no use. That's what you're saying, right?
Yeah, basically zero use. It's like trying
Hmm.
to predict the house price of a house price with like what is the temperature on that
Right,
current day, and
right,
like did it rain or
right,
how was the stock market? It's like
right, right.
there is no correlation.
Right. And the point you said, Dhananjay, it's for like, so say there is feature one and feature two is just two into that. So they
Yeah,
are correlated. That is of no use. That's what you
Yes.
said, right? Yeah.
there is somewhat of a correlation between those two. That's like
Yeah.
cross correlation between each.
Yeah.
That's also somewhat useful, but not as useful as this.
No, no. In that case, we already there is no information that we get by
Yeah.
having two separate features. Now we just need one feature for that.
Mm.
So if that is like
Yeah,
perfectly correlated, then we can just remove that and
yeah, we
then
can
do.
remove one of them. Yes. So we can check correlation between features to eliminate, and with the features, with the feature and the target value
Target.
to somewhat see what is needed.
Yep.
Yeah.
Okay. So I would like to jump into just like a simple linear regression model, like
Yep.
how it works and such. So the key idea here is like iterative learning. So where does the learning come from, right? Machine learning. So how does it learn? Well, the model starts with the initial guess and repeatedly makes predictions and checks how accurate those predictions are and adjusts itself to reduce errors. And the cycle continues until its cycle continues until it reaches a satisfied amount of in output, basically good enough output that we can predict what we need or classify what we need. This process often mimic how humans learn by trying, making mistakes, and understanding those mistakes, then improving based on that understanding. It's a very simple but a powerful method that we can iterate upon and make it more powerful.
Hi Anup.
So,
So we just started our lecture a few minutes back.
Okay, yeah, I'm so sorry. I
Yeah,
just
no
got
worries.
last minute.
You can just give a 2 minutes brief about what we were
of course.
talking today, so that we
Thank you.
can follow. So we were mostly looking at what is machine learning and what is its difference between simple algorithms and what is its difference between AI.
Yeah.
Okay.
Okay.
So so AI itself is like it's a broader field, and machine learning is like where the model will learn. So any intelligent algorithm, we can say it as artificial intelligence, but machine learning, in that there will be some learning involved.
Hmm.
That's the things we were discussing, and he was trying to explain it. There are different types of models: supervised learning, unsupervised learning, and reinforcement learning. And then we went into linear regression model, and these are like the steps. And yeah, you can continue now.
I can briefly explain what the steps are. So first we set an initial value. It may be like an educated guess of what we need. Then we have a prediction function. Here it is linear regression, which we'll get into. And there is something else called a cost function, which uh, looks at this prediction and sees how right or wrong it is. And based on that, we update the parameters. If the parameters are good, the predictions are good enough, we converge the parameters and we get an end result. So basically, it's explained here. The starting point of the process, set the initial value and such. So
Okay. Okay. Just a quick check. Are we recording this session? So maybe I can refer the earlier part.
I'm trying to
yeah,
record, but I'm not sure if the voice is correctly recorded. I'm screen recording and given the microphone. Yeah, I'll
Mhm.
have to see.
Okay.
Hopefully.
No problem.
so I think I gotten a bit ahead of myself. I think first we'll cover what a linear regression model actually is. So it's actually somewhat of a statistical model, which also comes under machine learning technique. So it tries to find a relationship between a dependent variable and one or more independent variable. In simple linear regression, it's only one independent variable. Say we're trying to predict the sale of an ice cream. How much ice cream you sell in a day based on how hot it is. And you try to plot this on a graph. So the aim is to find a linear relationship between input variable and the output variable. Output variable. So how if it's like how much of one increases, the other increases should be linear, as in there shouldn't be something of like a spike in, let's say, after the 10th value. So the basic equation is represented by y is equal to mx plus b. So that's basically the equation for the line where y is the dependent variable, x is the independent variable, and m is the slope, b is the y-intercept. So if there's a great resource that this is a great resource if you want to have a deeper understanding of linear regression, which I'll share this with you. So here we'll actually see what the things are. See these yellow dots, those are like the actual values of what we are trying to predict. And this blue line here is the actual value, is the prediction that we are trying to make. This is a line because it's a linear regression and the relationship between those two variables should be linear. The equation for that is y p theta plus p0 plus p1 is equal to x. P0 here is the y-intercept. This has a lot of like other names, but basically it just means how much of y changes if there is no influence of x. So let's say how much ice cream do you sell without how without zero influence of temperature. Um, and P1 is basically the slope P, and okay. Well, this is a better explanation. Dependent variable y is basically what we are trying to predict, and it depends on the independent variable x. In a real world scenario, it could be something like the price of a house, the weight of a person. And independent variable. This variable is what we use to we try to make the predictions with. It's also known as the predictor or the feature. Basically, we talked about features, right? And x is the feature here. If you have more than one feature, the x will be like, if here it's beta 1 plus x. So if you have two features, it will be beta 1 x plus beta 2 x, and so on. Beta 0 here is the intercept. So this term represents the value of y when x is 0. This is where the regression line intersects the y line. It allows the model to fit the diagram. And beta 1 is the slope or the coefficient of x. It's how much x is scaled based on y. This term represents how much y changes for 1 unit in x. It measures the strength and direction of the relationship between x and y. So I've taken up until now, but do you guys have any doubts?
One doubt, like which you were talking about just now, like say there is two features, so it'll be slope into that x feature, right?
I should mention if there is only one feature, we plot it in a 2D graph. If there are three features, we plot it in a 3D graph, and
Okay.
we can only plot it until 3D graph, and after that we can mathematically represent all of this in dimensions, but we can't graphically represent them.
Okay.
Like the equation I showed you, right? That can actually be used for how many features you have, but you can't actually represent them besides like three dimensions. Do you guys have any other doubt?
Maybe you can explain it in terms of cost function, how the line gets fitted.
Cost function, I haven't done much of that.
Okay.
Basically, what I've learned is the cost function. Oh, yeah, of course. The cost function for a simple linear regression is a bit more complicated, but it's easily understandable if you get the underlying the meaning behind it. So what the cost function actually is trying to see how much of our data, how much of our prediction is actually right. 1 minute, guys. Sorry about that. So the cost function is where basically the learning part comes in. The equation for the cost function might seem a bit scary. What does this all mean? But let's go through this, right? So the m here is basically the slope of the line. So, and the b is the y-intercept. So we've seen here, right? So basically what we do in simple linear regression is try to fit this line so that we make the best predictions. So say this line is almost close to all the data points and such that if we do a prediction here, this will actually be the best prediction that we can get out of this. So how do we make this best fit line? Well, we control two variables here, the intercept and the slope itself. The intercept is basically how high this line is, right? And the slope is like how the angle of the line itself. So how do we find the best of this? We first start with like a random variable. Let's say slope of the line is, basically we can also take like an educated guess on what the slope of the line is and what the y intercept is, and we put that in an equation here. So the first part of the equation, let's ignore it for now. So this thing is basically just a summation, like how many variables we have. Let's say at how many data points we have actually. So let's say we have 10 data points. We do this thing for 10 data points. So it is why I here is the actual value of that data point in that uh, data point, and we try to predict that given that we have this slope and this intercept, and see how what is the error or cost function comes out to be. If the cost function is very large, it means that our prediction is very bad. And when the cost function becomes very small, it means that we actually predicted, our prediction was actually very good. So how does it this become small or big based on, is basically based on that we are minusing, we are subtracting the prediction with the actual value, which gives us some amount of value, right? So if the value difference between the prediction and the actual value is great, we'll and we square it so that the errors are greater for some. The squaring is basically used so that we can for better interpretability and such. Then we'll see G and M and D, right? This is basically our cost function. N here is the number of data points we have. Y is the actual value of the ith data point, and xi is the independent variable for that ith data point. M is the slope and y is the intercept. So we try to get the best M and B here. So that's what we basically try to get.
Mhm. I guess the squaring is done to get the absolute value, so that if
Yeah.
there are like multiple dimensions in this, or like multiple points are there, no? One can become positive, one can become negative.
Yeah.
So in
That
that
is
case, what will happen is like one huge error in the positive side and one huge error in the negative side could cancel each other, and that could become the best fitted model. So to
yeah.
avoid that, we are actually using the squaring.
Yeah. The reason we use the 1 by 2n is to normalize the cost by the number of data points. Without it, it will be like a very large number, which isn't really interpretable by the model. By by the model. And 1 by 2 is included to simplify the derivation calculation in gradient descent, which is where this is actually used. Gradient descent is a bit more complicated, so I haven't covered this here. So let's see the difference between AI and ML. So you guys might have what is the difference between AI and ML, right? AI is like a broader field of intelligence, intelligent machines that can perform tasks. Let's say if you have what is like a classification is intelligent AI could be something like taking decision based on certain parameters, certain things that you give. It's hard coded. That means that when you do something, wait a minute. AI is basically like a broader topic that can perform tasks that are like here intelligent. Say you have like a you have want to classify something based on if it has it is more than 3 or less than 3, and there are like a lot of inputs and such. AI can be used. ML is like a subset of that, that focuses on algorithms and statistical models that enable the computers to improve their performance through experience. That is basically data. the more data you give it, the better it gets. And the key feature here is that it's not explicitly programmed and such that we don't have, it's not hard coded. So there's not like if this X do Y, adapts to what the data is actually. But the con of this is that it's very dependent on the quantity and the quality of data. So if you have like very bad data, the predictions will actually be very bad, and the quantity also matters. If you have like 10 data points, it will do far worse than if you have like 100 or 1,000 data points. How each work, like how does an AI model work and how does an ML model work? ML uses like rule-based system logic and search algorithms, and AI is not always dependent on data. For example, like as expert systems in past were based on hard-coded rules. The examples can be like virtual assistants like Siri, Alexa, and like self-driving cars are a good example of AI systems. ML specifically relies on data. It uses algorithms like decision tree, neural networks, and SVMs to identify patterns and make predictions. Basically, ML is tries to find patterns and predict these things. It
I think
also improves
here
on feedback.
virtual assistants like Siri, Alexa,
Yeah,
they might have, there is some machine learning involved. So here specifically it's AI, but it's also ML, right?
the amount of ML is significantly less than like chatbots like ChatGPT.
Amount of.
Yes, the amount of like how much they use ML algorithms are very significantly less. They use like natural language processing to understand what we are saying,
I think that's
but there
is a
are
miss. I still doubt that. This
No,
also
I
ML.
think he's right because this what is this? Any of these chatbots or anything. So basically, even if it's something like a virtual assistant, they will have some data. Maybe they would have indexed the whole web, so that data they have. But in terms of how they deliver the question answers to what people ask, it is based on similarity and natural language processing.
Yeah,
Like they
that I
convert that into.
that is there, but in
Huh.
that case, all the inference, there is no learning involved, right?
yeah, it's
Although,
Oh,
just like
whenever there is an inference, it's just matrix multiplication, right?
yeah,
See,
it's
in that
what
case,
do
basically
you
both
say
are
by
same.
inference?
Whenever there is inference, even in recommendation systems or linear regression, whenever we
Hmm.
do an inference, it's just it multiplies with a matrix and gives output. Similarly for this Alexa, Siri also, but there is a, it's AI, but it's not ML, but it's ML and AI, but we can't say it's AI but not ML. But there are
yeah.
some other
It,
systems like which is totally hard coded. Those can only be said as like only AI, not ML. But Siri,
Yeah.
you
Alexa,
mean
all
to
those.
say, in Siri or okay, any of these chatbots, if there is some input that the user is asking, so i- where is the inference coming into picture? Because if they ask, it will just do a similarity search and give the result.
It it does not. I don't know if it just do a similarity search, but that
Hmm.
similarity search, it has happened through some learning, right?
What is it's already fixed, yes. So how these chatbots are designed, they have some for how they get the information that is there. But when they're interacting, it's just through some NLP based algorithms, like similarity and all
Yeah,
that.
in that case, we can't say it's not ML.
If you
NLP
look
strictly
at,
speaking,
go on.
like
We,
ML strictly speaking isn't actually NLP strictly speaking isn't actually ML. It's just like somewhat of AI and ML. It's actually a big mix.
This NLP similarity search is like they convert these sentences into embeddings and they do the cosine similarity. That's when they see
Yeah.
which is similar, and then they get the lesser, whichever has lesser cosine, I mean more similarity, it will retrieve those. So there's no direct algorithm involved in terms of any ML model.
I'll have to see, I guess. But I strictly
Mm.
believe it's ML itself, Siri and
Yeah, I think
Alexa.
it's a good question to explore.
Yeah.
Yeah, we can
Should
leave that
we?
and move on, I guess we can.
Okay. So like here ML in general, like I tries to identify patterns and make predictions on said patterns. So when you have a lot of data, the ML algorithm tries to find a different patterns. Here in linear regression, it tries to find how much of X is X influences Y, and based on that, we try to make prediction. The more amount of data we have, that is to say, the more amount of like data points, actual data points we have, the better the prediction line will be. We have seen that this right. If how the end here is the number of data points, and the larger the number of data points, the better the predictions will be. So the basic examples of ML can be spam filters actually. Surprisingly, spam filters use ML algorithms and has been using them for a long time. It was using something called Bayes' theorem, and recommendation engines also use ML algorithms to give the best search results. And chatbots like ChatGPT are built on ML models like transformers. So let's
Yeah,
have a
this point which he said, this all these virtual, it's built on ML models. So it is built on neural networks transformers. So when the training and all is done for these virtual assistants, they are trained on heavy. For that, we need ML
Hmm.
models.
Yeah.
Yeah, I think that is right.
So I think I should
Yeah,
have given
continue.
like better AI
No, no, no.
example.
It's good. It's good that this point was made.
But there are
No, do you
something that
have?
was created by IBM without any training at all. That can be told as like
Hmm.
AI, but not ML. Where everything, most of
Hmm.
the things were like hard coded. I forgot its name, but IBM had created something without any
Hmm.
learning from data.
Learning. Okay.
There's something called IBM Watson.
IBM
Is it that?
Watson is
That is different, no?
yeah, that is different. But I will see. I have written it somewhere. I will send it in the group.
Mm. So let's dive into the most popular ML models. First one being supervised learning. When anyone starts to learn ML, they usually begin with supervised learning. And because it's like the easiest one to start with, because it has labeled data. We've seen linear regression, right? That comes under supervised learning actually, since we actually know the output for the data points we give. Like, let's say house prediction itself, right? We have certain amounts of data points where we know the actual price of the house, and based on this we try to predict the next data point. So the basic examples of supervised learning are classification and regression. It tries to make a function that maps the input to the correct output. uh, the distinct characteristics of supervised learning is that it always requires labeled data. Supervised learning cannot happen without labeled data. It has like very clear evaluation metrics that is very interpretable. That means that we can easily understand what is going on and try to improve it easier. Useful for prediction tasks. Basically, if you want to predict certain things, supervised learning is where you find them. Classification and regression are like very simple models. If you want to go a bit deeper, you have like support vector machines and decision trees. Decision trees is something of like make basically in its name itself, like making decisions based on certain criteria. So if let's say the decision on which it makes is actually learned. The example of supervised learning is to classify an email to either it's spam or not spam. So we basically give certain data points where we know which email are spam and not spam, and we use that to train a logistic regression or a decision tree to basically predict if the next email coming in will actually be a spam or not spam. Here, the algorithm learns from label data to predict the new and unseen emails. If you are wondering what logistic regression is, it is somewhat similar to linear, but it's not actually regression. Uh, Unsupervised learning. Unsupervised learning tries to find patterns in unlabeled data. So if you have data which doesn't actually have like output feature that we want to predict, and is just something we want to classify or cluster, is where we use unsupervised learning. The goal is to discover hidden structures or relationship between the data features. Let's say a company has like 5 features, and they want to see how these features affect each other, and how correlated these features are. So we talked about EDA, right? Supervised unsupervised learning is used for EDA to discover these correlations. It can be used to discover unexpected patterns that might not be something that we see the first time around. Example is customer segmentation. Group customers into different segments based on the purchasing behavior. So if you have different types of customers and you want to cater to one specific customer base, you have to segment them to see which customer base you want to uh, basically attract. Unlabeled data set with features such as purchase history, frequency of purchase, and amount spent can be used for segmenting the customers. The one of the most popular, the best known algorithms are k-means clustering and hierarchy clustering or principal component analysis. PCA is also used in several other things. How it works is basically the algorithm identifies patterns and similarities in the data to group customers into segments with pre-existing data labels. So we make certain data labels, and the algorithm tries to put these into those labels. And
Just a
last
small
but
thing
not
I'll
least,
add about PCA. So PCA is like done like a pre-processing step as well. If we have a lot of dimensions, like it's used as a dimensionality reduction technique as well, where we extensively use PCA if there are so many dimensions, so that the model will not get confused with so many features. And it's
yeah, it's also yeah. You can also make it useful for like interpretability. If it has like 5,000 dimensions, we could theoretically compress it down to just 2 dimensions for more interpretability to see what is the relationship between each labels, each data, uh, each feature.
yeah. So something similar we had done while I was working in Ikigai. So for time series data, there was like more than 5,000, 6,000 SKUs. So to identify similar SKUs and categorize them, so each of those time series data was like done PCA, and we would plot them into a two-dimensional graph to identify the clusters of SKUs together, and then train like a time series model on each of those separate clusters. So that earned like a very good result.
So, when you do PCA, is there any data loss or anything?
uh,
Information loss, not
information,
data
so
loss.
information, so
Okay.
what we do is there is some, I forgot its name, so we plot like we include number of number of components we decide based on how much
Hmm.
information we got through this number of features, like this number of
Okay.
PCA components we can plot that. I forgot its name, but there is something that we plot before deciding on the number of components
Hmm.
from we choose to use in our model. So we choose like 95% of the information is retained, or 90% information is retained with these many features, and then we use that many number of components
Okay.
from the PCA to train the model.
Okay. Okay.
So the third model that I would like to cover is reinforcement learning. I think this is the most like interesting model, since like where would you use like the question that comes to mind is where would you use reinforcement learning? Like, if you want prediction, you use supervised learning, and if you want class like to cluster things, you use unsupervised. So where does reinforcement come in? So reinforcement is basically used for a very complex and dynamic environments. The example that I could give you is chess games. We can use a chess. The first move after the third move from a chess game already creates like more than 100 million possible moves. If you try to use supervised learning to predict the best way to play this, it will be like super complex and take a lot of time. So that's where reinforcement learning comes in. This is the, in my opinion, the most human like in the learning. The algorithms learn through interaction with an environment. So here in the example, the environment would be the chess game itself. And the goal is to maximize a cumulative reward signal. Basically, have getting positive feedback. The distinct characteristics of reinforcement learning is that it involves sequential decision making. So first it makes a decision, sees how it works out. Based on if it's good or bad, it makes the next decision and so on. It balances exploration and exploitation. Exploration means that it tries to find new ways to the same problem statement. Exploitation is using the same way of doing the use solving the problem statement. But if you use either one too much, it will be bad. So suitable for complex and dynamic environments, as I've said. So this is a very simple diagram of how an agent here being the model, learns. So the agent first takes an action, and the environment creates a reward, be it a positive reward or a negative reward. And based on this, the agent creates a new state. The new state being the the new state here is basically the next step on what we want to take. So here the example is training a chess playing agent. The task here is to teach an agent a computer program to play chess and make optimal moves to win the game. The agent interacts with the chess environment by making moves and receiving feedback in the form of rewards or penalties based on the outcome of game, be it winning, losing, or drawing. The algorithms used here are a bit more complicated. I myself haven't got into it are Q-learning, deep Q-learning, Alpha Zero reinforcement learning specifically designed for board games like chess, and much more. How it basically works is the agent explores different strategies, moves through self-play or against other opponents. So it can play against itself or with other opponents and see explore different strategies. So here the exploitation and exploration part, right? Exploration is like exploring new strategies, while exploitation is like using the same strategy. So if you use the same strategy for too long, there might be a better strategy, but you might never know it because you're using only the one strategy that you know. If you explore too much, you are not putting much effort into each strategy to see if it works or not. So this is a simple introduction into what is generative AI and how it is different from classical machine learning. Generative AI is like a subset of ML, which in on itself is a subset of AI, is used to create data that is similar on which it was trained on. Unlike traditional machine learning models that focus on prediction or classification, generative AI learns the underlying pattern of these data and try to generate new data. So image generation, yeah, they say that image generating models pirate like other creators, right? The reason being is that it's not totally original. It always is similar to the data that it was trained on. So the ChatGPT being is a type of generative AI. It was trained on like millions and billions of text data, and it tries to predict, create new text based on our input. So key features of AI is creation of new data. It creates new content like ChatGPT text for ChatGPT, images for DALI, music, and even code. GitHub Copilot is an example for AI, generative AI that creates code. Learning data distribution. Once a generative model is trained, they can sample this distribution to create new data points. Generative AI often uses unsupervised or supervised learning, where the model learns from data itself without like needing labeled outcomes. So one use case of self-supervised learning is that generative AI doesn't actually need labeled data to create these new data points. Video generation is like a new advancement in generative AI. We've seen a few that has come along, but hasn't reached the maturity that image generation and text generation has. The Sora from OpenAI is one of the use cases. So how is generative AI different from classical ML? Generative AI is a subset of ML called deep learning, but ML is a subset of AI. Classical ML is usually focused on prediction and analysis and even classification. And one pro of working with classical ML is that it can be used with smaller and structured data. It's very simpler to interpret and easier to understand. But on the other hand, ML techniques usually require a very large amount of data, usually in the millions and billions, to understand these underlying structures. Focus on creating new data is what generative AI does. So that was basically it.
Nice. That's
Yeah,
good.
nice. Thanks for sorry.
I do
Covered
something.
quite a lot.
Nice presentation.
Yeah. Thanks, Faraki.
If you have any doubts, you can ask.
Just one thing, like to summarize kind of some simple stuff. Like if we try to represent in a Venn diagram, AI is one, the entire thing. Within that, we have ML,
ML. In
and
that we have
we have yeah,
deep learning, DL.
and reinforcement learning.
Reinforcement learning is the most human-like, in my opinion, since it learns from an environment. Environment being anything. In the example I gave you, the environment was the chess game itself.
Mm-hmm.
So the reinforcement learning comes under ML only.
ML, yeah.
Yeah.
Got it. Okay.
And coming to the cost function, Fahad, you explained, right?
Yeah.
So what does it signify? Like,
The cost function is trying to trying to make the best two values. The values being the intercept, y-intercept, and the slope itself.
okay,
So we try to predict the best value for this with
okay.
the cost
So,
function.
so as if the value is higher, we can say that it is more accurate, or
It is
like that.
it is versa. So
Okay,
if the cost function is very low, it means that our line is very much best in the case we are using.
okay,
The cost function tries to find the best y-intercept and the slope.
got it.
So we can generalize like in any ML model, we are trying to minimize the cost function.
Okay,
Yeah,
So
we try to yeah.
yeah, so by minimizing the cost function, we will arrive at like a suitable model. So that is why we use something called gradient descent. So the gradient descent algorithm tries to so there is when it's two dimensional, it's very easy to go to the you know the maxima minima, right? You try
yeah,
to find out the minima of the curve.
okay,
It's not exactly fitting function, so we try to jump around using several uh, methods to find out the least minima value.
got it. Yeah, and also coming to reinforcement learning. So, how does the rewards like? What does it do to the model? Like, what?
If the reward is positive, that means the current strategy it's doing is working. So it
Okay,
tries to improve upon that. If the reward
okay,
is like negative, it tries to do something different in the other direction.
got it.
I myself have just gotten into it, so my answers might be like a bit vague.
Okay, okay,
No
No,
problem.
no, it's correct.
no
It's
problem.
fine.
Anup, do you have any questions, Anup?
At this moment, no, Dhananjay, I'm so sorry. I'm a little lost here because I join in between, and even ML that requires a lot of practice or maybe a prerequisite as a learning. So for me, to be very honest, it's a little complex.
No, you can ask anything. I'll start from there itself.
No, that's fine. Maybe uh, I'll have to explore a little bit more on this ML part, introduction to ML. Then probably I can ask the concrete questions and relevant one also.
Do we have enough time to like cover the first part again? I think that is very easy to understand. Oh, Anu?
Depends upon everyone, but maybe if we have the recordings, Dhananjay, by any chance.
I'll see. I'll stop